Hi, I'm Chem's best friend, and if you need any chemistry help, the information is on the bottom of your screen. So, are you ready to learn about energy? We're going to do this video focusing on calorimetry, and then the next series of videos will be all about energy. So, let's go to my screen. Have a look at this. There's all kinds of different forms of energy. There is thermal energy, radiant energy or sunlight energy, light energy, chemical energy, nuclear, electrical, gravitational, mechanical. You probably heard of kinetic energy. That's also tied to mechanical energy, energy of movement, like you riding on a bike. And potential energy. That probably should be called here gravitational potential energy. So there's all kinds of energy. How do we deal with it with chemistry? Well, I would like you to think of energy as nature's currency. So whenever we will be talking about exchanging money, if I give you $20, I just gave lots of information to you. Number one, I told you how much I gave you. Gave you 20. And now 20 what? $20. You should also include always a unit. And then I gave this to you. So I lost $20, but you gained $20. So you always have to include a sign. So whenever you're talking about energy, think of money exchange, so energy exchange, and you need to include these three things: amount, unit, and sign. Okay, let's go to first law of thermodynamics. So first law tells us that energy cannot be created or destroyed. It can only be changed, converted from one form to another. And that means that all the energy at the beginning of the universe, when Big Bang happened, is here now. All that energy is here. It was just changed from one form to another. Okay, what are the units of energy? Let's go here. So the basic unit of energy is calorie. That's the unit people came up first. It's really easy. You take 1 gram of water, and how much is 1 gram of water? Let's think of it like you're playing a game, Monopoly. You have dice. That dice is 1 centimeter on each side. So that's 1 centimeter cubed. That's 1 milliliter. And density of water is, because you will see it's 1 gram. So you're heating up the amount of playing dice of water, and you want to heat it by 1 degree Celsius. So how much energy will that be? People say it's 1 calorie. But 1 calorie is not an SI, System International unit of energy. That is a joule. And this is going to physics, and these are the units of a joule if you talk about physics. But anyway, for us, what's important, this is the conversion factor. 1 calorie is 4.18 joules. And keep in mind that this is 1 calorie with a little c. So 1,000 of these calories is 1 big calorie, 1 big C calorie. And these are the calories you see on a bags of cookies that you buy. So if you say 1 cookie is 100 calories, they actually talking about these calories, which is then actually 1 kilocalorie. So these are the units of energy that we need to know. And let's keep going. Let's learn more about energy. So here is some definitions of energy. Energy is work plus heat. Think about it is, why did you eat lunch? Well, you ate lunch to be able to move, run around. So that's work. And you also ate lunch to keep your body temperature. You're producing heat. That's why we eat, energy, right? Why we eat food. So change in energy, delta E, is your work, and Q is heat. We also talked about first law of thermodynamics, and energy can only be converted from one state to another. So whenever an energy of a system, if a system gains energy, the surroundings have to lose energy. So it's only energy transfer. But the problem is that delta E, change in energy, is actually too hard to calculate. But here is the thing. We have this definition of enthalpy, and how did we get that? It's more involved. But enthalpy is energy plus P change of volume work. And at constant pressure, which will be your classroom environment when you do energy calculations, when you do labs at constant pressure, energy is very closely related to enthalpy. So enthalpy is just heat. Enthalpy is heat at constant pressure. You will be measuring heat change. So it's very close to energy. It's not exactly. But at constant volume, which is a BAM calorimeter, chances are you will not be working with that in a classroom in a normal high school setting. But change of energy of a reaction is your heat at constant volume. And in this case, enthalpy is change in enthalpy is change of energy at constant volume, because there is no change in volume. So this term becomes zero, and energy then is enthalpy. So it's easy for us to just worry about heat change versus volume, heat change. So how do we measure heat change of a reaction? We're going to use a calorimeter. So calorimetry is the science or act of measuring changes in state variables of a body for the purpose of deriving the heat transfer. This is important. You're going to be measuring heat transfer associated with changes. They can be change in state. There can be chemical reactions, right? That's what we will be doing. Physical changes, phase transitions. So calorimetry is performed with a calorimeter, and in this case, this is a constant pressure calorimeter. So what is a constant pressure calorimeter? Well, the best thing to do is think of an isolated coffee cup. So in science classrooms, we will probably use styrofoam caps. They are a very good insulator because styrofoam caps traps air, right? Little bubbles of air, and air is a great insulator. So you're going to have double styrofoam caps, and usually put a lid on it. You will have a thermometer to measure temperature change, which will be a heat change, and you will have a stirrer. Sometimes a thermometer is used as a stirrer. Okay, and we're going to measure how much, this filled with water usually, how much water did it get colder, did it get warmer when you do a reaction. So let's go a little bit more. And the amount of energy required to heat a substance will depend on three things. It's going to depend on amount of substance, which is the mass. It will depend on what type of substance you're heating, which will be specific heat capacity of that substance. Each substance has its own specific heat capacity, just like each substance has its own specific density. So that's also a physical characteristics of a substance. And also how much we want to heat a substance. How much do we want to make it super hot or just a little bit warmer? And the equation we will be doing, and remember, this is my heat, and at constant pressure, this is my enthalpy, right? Is then equal to mass, amount, times specific heat, type, and how much, times the change in temperature. Now, we will be talking about delta T. So if you are using degrees Celsius or Kelvins, it's the same thing. You can use both scales. The reason is we will be talking about delta T. And one change degrees Celsius is actually one change of Kelvin degrees. So here we go. So remember this equation. This is very, very important equation for us. And here is a table with different substances. And here is their symbols or, chemical formulas. Brass is an alloy. It doesn't have it's a mixture. So there's no formula for it. Same thing with granite. And here is the specific heat capacity in joules per gram per degree C. And here is in calories. So for water, we said that specific, that's calorie is how much it heats 1 gram of substance by 1 degree C. So that's 1 calorie, but then it's also then 4.186 joules for water. And you can see quickly, and this is a very, very nice visual representation of this, that water has very, very high heat capacity. It's amazing. It takes a lot of energy to heat up water, which Actually, I don't want to really get into it, but this is why life is possible on Earth, because like 72% of Earth is covered by oceans, and it's very hard to heat it up. And this is what allows climate to exist on Earth, and it allows us to live. Otherwise, we would have extreme temperature swings. So water's extreme high heat capacity is amazing, but it also makes it a very weird substance. So let's keep that in mind. Okay, let's keep going. And here is just a comparison. Again, water being very, very high in aluminum. And that means if you add the same amount of energy to water and aluminum, water will not change that many degrees. Aluminum will become much more hotter. So think about this. Yes, water requires a lot of energy. It resists change. The bigger the number here, the more it resists change, the more you need energy to raise the temperature up. The lower it is, the easier it is. That's why metals have very low specific heat. They get hot really quickly. Okay, let's do some questions. Let's do a little bit of problems. How do we deal with this equation? How do we do with calorimetry? And here is a problem. So gallium is a solid metal at room temperature. It melts at 29.9 degrees C. If you hold gallium in your hand, it will melt from your own body heat. How much heat must 2.5 grams of gallium absorb from your hand to raise the temperature of gallium metal from 25 degrees C to 29.9? So you are going to raise it just to its melting point, and it will still be a solid. And the specific heat capacity of gallium is 0.372 joules per gram per degree C. Now remember, this is the equation we have to use, and let's actually do this problem. So it's asking you how much heat, right? How much heat? Well, heat is Q. So I think, let's see if I have everything. Do I know my mass? Right? Do I know my mass? So what's my mass of my gallium? Well, that's 2.5 grams times, what's my specific heat of gallium? 0.372 joules per gram per degree C times, well, now I have to deal with this delta T. And this is important. Let's deal with what does delta T mean? Delta means change. That means I always have to put my T final minus T initial, my final temperature minus my initial temperature, right? Change is always final minus initial. Always do that. The sign will take care of itself then. So times, what's my final temperature? I want 29.9 minus, what's my initial? 25.0. This is degree C. Yes? Now, let's look at my units. Grams here cancel out. Degree C on top, degree C cancel on the bottom. What's left? Joules is left, which is a unit of energy. Let's plug these numbers into a calculator, and if we plug these numbers into a calculator, we get that Q equals 4.557 joules. But remember, we have two sig figs, right? Remember, this is two sig figs. We should then have two sig figs answers. So I'm going to say 4.6 joules. Now, maybe I should make it clear that this is positive number. Positive. So what does that mean? That means 4.6 joules have to be absorbed by gallium to raise its temperature from 25 degrees C to 29.9 degrees C. So, do we feel comfortable using this equation? Are we ready for a little bit bigger challenge? I think we are. Let's go to this problem. Here we go. This is a little bit more challenging. Here's a picture. We're going to have 15.7 grams of aluminum metal, black. We will warm it to 53.2 degrees C, so it will be pretty warm. And we're going to plunge it into our coffee cup calorimeter, and that has 32.5 grams of water, and that water is 24.5 degrees C. So we're putting a warm aluminum black into cooler, a little bit like room temperature water. The aluminum and the water are allowed to come to thermal equilibrium. So what does that mean? Well, heat always travels from hot to cold, always one direction. So the hot block of aluminum will lose heat, and then the water will gain heat. So we are going to assume no heat is lost to air, to environment. It's just a perfect heat transfer. So the question is, what's the final temperature of water and aluminum? All right, let's solve this problem. Before we do solve this problem, we need to talk about system and surroundings. Remember, we talked about how energy lost by system is then gained by surroundings, or by vice versa. Energy lost by surroundings will be gained by system. So, because energy can only be transferred, cannot be created or destroyed. So you need to decide what's your system and what's your surroundings. And many students get things wrong because right there, they cannot define system and surroundings. Many students think that, oh, whatever happens in a coffee cup in my calorimeter is my system, and then everything outside my cup is my surroundings, which is what you would probably think. No, imagine the whole coffee cup is the universe. Your system and surroundings is everything inside that coffee cup. So let's write this down. Let's write this down. This is important. So heat lost by my system is going to be perfect heat transfer. Heat gained by surroundings. But there is a problem with this equation. And the problem is, just look at the words lost and gain. Do they mean the same thing? No. You will say, wait a minute, they are antonyms. They mean the opposite. So how do I make loss equal to gain? Well, if I have a negative opposite of loss, I'm going to have a gain. Or if I erase this, let's erase this. If I have negative of gain, opposite of gain, I will have loss. So here's the thing. You are going to put a negative sign in front of one of these sides, and it doesn't matter. I just like to put a negative here. There you go. So negative of heat lost of a system is heat gained by surroundings. So now the question is, I need to define what's my system, what's my surroundings. Okay, I'm going to define my system as aluminum. And I'm going to define surroundings as my water. And everything is the universe, okay? So there will be heat, let's draw this. There will be heat going from my system to my surroundings. This will be my heat transfer. All right? Does that look good? Is this making sense? I hope so. Now, here are some tips how we're going to work here. So usually, so the final temperature of water and the metal will be the same because they will reach thermal equilibrium. So they will exchange heat until there can be no more heat exchanged, right? So many times you will have a problem where a metal is first placed in boiling water, where boiling water is 100 degrees C, and then a really hot metal, 100 degrees Celsius, is then plunged into much cooler water. In this case, the problem is the metal is just warmed up to 53 degrees, but many times this is the case here. Water has a 1-to-1 density, right? So mass to volume ratio. So if you have whatever milliliters, 25 milliliters of water, you can assume you have 25 grams of water because of density of water. Some specific heats will be given to you. Sometimes temperatures will be given and you'll be asked to calculate specific heat. And remember here, the heat lost by system will be heat gained by surroundings. It has to be opposite signs. So just keep that in mind. So we're going to start this problem. Before we start this problem really fast, I am going to write down things that I know. So system is my aluminum. Water is my surroundings. I'm going just to write this a little bit less. So system is my aluminum. surroundings is my H2O, water. And let's write down everything we know about aluminum. And let's down everything we know about that water. Now, what do I mean? Let's down everything, remember what I know. Remember our equation? What's heat? Heat equals mass times specific heat times delta T, right? This is my equation. So let's write, do I know mass? Do I know specific heat? Do I know T initial? Do I know T final? Let's write down everything we can about aluminum. Let's write the same thing about the water. Mass, specific heat, T initial, T final. Yes? Okay. What's my mass of aluminum? All right, that's 15.7 grams. What's my specific heat of aluminum? Well, I can go right here. Yes, right here, and I can check my specific heat of aluminum. It's 0.897. You can see it highlighted. So let's write that. My specific heat of aluminum here is 0.897, and this is joules per gram per degree C. My initial temperature of aluminum is 53.2 degrees C, and my final temperature is X. I don't know. That's what I'm trying to find out. Let's find out. Let's write whatever we know about the water. Water is, we have 32.5 grams of water. Specific heat of water is 4.184 joules per gram per degree C. We are starting with 24.5 degree C water, and this is going to be the same. They are going to come to thermal equilibrium. That means this has to be the same as this, right? The final temperature will be the same of both my system and surroundings. Okay, here is all my information, and let's solve this question. How do I solve what's the final temperature? Okay, let's write what we know one more time. Remember, negative heat lost by system equals heat gained by my surroundings. System is my aluminum, surroundings is my water. Heat is Q, right? Heat is Q. So I have to say, you know, heat, Q is Q, right? What is Q? So, well, Q equals my MC delta T of my system has to equal MC delta T of my surroundings. And I had that big negative. So let's plug in all the numbers. Let's deal with aluminum. I'm going to put a big negative. Just wanted to have it this side, this color. So let's go here. Nice. So I have a negative. And then what is my mass of aluminum? That was 15.7 grams times specific heat of aluminum, 0.897 joules per gram per degree C, times, well, what's my T final? That's my X. What's my T initial? 53.2. This is degree C. Close the whole bracket. And this equals, now let's talk about heat gained by surroundings. Surroundings is our water. So what's my mass of water? That's 32.5 grams times what's my specific heat of water? 4.184 joules per gram per degree C times what's my T final? That's X minus T initial, 24.5 degrees C. Let's close this. All right. So now I need to solve for X. So we're going, this is, yes, we're going to isolate X, solve for X. Let's do it. And we're going to do some algebra quickly. So I'm going just to plug in some numbers. If you, I'm just going to quickly multiply these two numbers first and rewrite this, multiply this and you know, rewrite this, and then I'm going to distribute. So really fast, some algebra. So X minus 53.2, and I'm just kind of remembering all my units will work out and this equals 135.98. X minus 24.5. I'm going to distribute this now. So I have 829 X, and this will be plus 74.921, and this is going to be 135.98 X minus 3,331.51, and we're going to quickly clean it up. So 3406.431 equals 137.388 X, and we're going to say, okay, well, then X equals 24.794. Let's talk about sig figs. That means my X has to be 24.8 degrees C. And there you go. That's the final answer. So is this making sense? Let's quickly look at this. Does this make sense? So 24.8 degrees C is my final answer. 24.8 degrees C is my T final. Let's think. Well, number one, I have much more water than aluminum. Water has 4 times as much specific heat capacity as aluminum. So aluminum dropped down around 25 degrees C, but water only gained 0.3 degrees C. Is this making sense? Yes, given that we have much more water, twice as much water, and I have 4 times specific heat capacity. So again, you need a lot more energy to heat up water than aluminum. So this is what this means. Okay, so I hope you learned how to solve simple calorimetry problems of metals being plunged into water. And I hope you understand a little bit more about energy. And in my next video, we will actually start talking about chemical reactions in calorimeters. So see you next time.